Got it. All right. So, hi, everybody. I'm Kalika Curry. I am an experienced IT professional. I've been working with data in some regard since about 2006. I have a passion for artificial intelligence and machine learning. And that's me in a nutshell. Today, we are discussing Chapter 9 in hands-on machine learning with Scikit-Learn, Keras, and TensorFlow by, is it Aurélien? Is that how you pronounce his name? Aurélien Géron?
Aurélien.
Aurélien. All right.
Yeah.
So let me share my screen here. There we are. Hit share. Can everybody see the screen?
We can see it.
Yep. All right. Let me see if I can figure out how to get a slideshow going. Let's do this. Oh. Doesn't want to let me do slideshow.
I think
apparently.
Windows, it's just F5.
Oh, there we go.
I mean, you can find all the different buttons and things, but.
There we go. All right. So we are leading a book discussion on Chapter 9, Unsupervised Learning. So what is unsupervised learning? So he pretty much described it as modeling unlabeled data. Now, previously in other chapters, we learned what supervised learning is, where you go through, you have a labeled data set, and you run predictions off of this labeled data set. Whereas unsupervised learning is very different. You have unlabeled data and you are trying to find information about this unlabeled data set. What we know, what he mentions about unsupervised learning is that it's got a high potential. There's mention about like a manufacturing example where you can identify certain things about a series of photographs taken in a manufacturing lab to determine whether or not parts are defective. Last week, we talked about dimensionality reduction, which is also a common form of unsupervised learning. And then he gives some types of unsupervised learning. He says, clustering is where objects are grouped together. There's anomaly detection where you learn, what's normal and to find out what's abnormal. And then there's this sort of density estimation, which is I guess a probability density function. And it's estimated the random process for an anomaly detection. Anybody have any other inputs that they would like to kind of jump in there about unsupervised learning?
I think one thing we can say at the beginning is that generally speaking, all the different unsupervised learning, techniques, they tend not to be your end goal. They tend to be a tool that helps you towards some eventual end goal. So it might be a tool that you use in feature engineering. It might be a tool you use for whatever reasons, compression, dealing with noise, but just getting reduced dimensions, just getting clusters, that's generally speaking not what people are interested in. They just use that as one building block to ultimately, classify things, ultimately, build a predictive model or forecast or whatever.
Yeah, I think they also mentioned using it for something for like getting insights about customers. So something of that nature where you just kind of throw everything around and you look at it and you say, okay, this group looks a lot like all the other groups. And then you can kind of figure out what to do about it from there, right?
Yeah, so I mean, super simple examples. You have a store and you have frequent customers, repeat customers, and then you just have, everybody else, right? What do your frequent customers look like? Is frequent for you 3 times a year, or is frequent for you, 20 times a year? And how much do they spend? And then maybe you actually find that there's multiple clusters that amongst your frequent customers, you have different kinds, right? You have big spenders, you have, people who come in and do a small amount every, whatever, right? There's different ways, yeah, that you can just sort of use clustering to help with exploring and understanding.
All right. So let's see if I can.
And
So,
I want to jump in and just add one more thing. So there's sort of a continuum of, there's not just unsupervised and then supervised. There's like kind of a range between that, where there can be unsupervised, semi-supervised, and supervised, and like anywhere in between. And a lot of the times, what unsupervised really means is just you don't have the actual target that you're interested in, but you might do something where you still kind of do unsupervised learning on the data itself. So like there's stuff like BERT right now where it's initially trained with no labels, and so it's unsupervised in a sense, but it's just learning from the data itself, and then eventually that builds into a very strong supervised system. But the unsupervised part is kind of the important beginning part. So the unsupervised can build into that.
what is BERT again?
So BERT is right now kind of the state-of-the-art text model, and the unsupervised part, or self-supervised or semi-supervised, whatever you want to call it, is basically it does this task where it looks at a whole bunch of text, and then it just on its own will remove words and try to fill in the blanks. And so it's learning from itself. We don't have any data necessarily. And in learning that task of figuring out what words typically go where by filling in those blanks, it builds a strong language model that can then be transferred to learning how to classify other things. But that's the gist of BERT, is it starts in that sort of unsupervised, self-supervised state. Yeah.
I would also add that, this whole unsupervised thing is, or unsupervised learning is got a lot of great usefulness because the vast majority of the data out there is unlabeled. So and it's not going to be labeled in the future. Nobody's going to nicely go, oh yeah, that's the dude that, this is a bad customer and that's a good customer. We're going to, nicely give you a binary division of this. You're not going to do that. So unsupervised learning methods, I think, are probably more important to some degree than supervised learning methods, because the amount of data just out there is unsupervised. And we don't really know what if there's classification, what the classes are going to be. We just sort of bump into them and manipulate them as we go along. So I think this is probably, very, very important section of this book.
All right. Are we ready to move on? Great. All right. So we're focused on clustering today, because as we mentioned earlier, this chapter is rather long. We have 2 parts in chapter 9. We have the clustering division, and we have this Gaussian mixture division. And with this being such an important topic, we thought it was best to split it up and kind of let us have this discussion around clustering. So what is clustering? He mentions that there's no real definition of what a cluster really is. If you want to talk about a cluster, you have to consider a context. We know that in a clustering model, you're assigning instances to groups, and it's similar to supervised classification models, but without the labels. And then you have, that there are different ways to cluster. You can use a random point as a centroid. You can run around in a circle. There's a bottom-up approach. There's a top-down approach, which is kind of hierarchical. I can never pronounce that word right. And of course, there's so many different ways. Let's see here. Oh, all right. So we'll see some of them a little later in the course. Does anybody have anything they want to touch base on before we move forward about the why clustering?
No, I think I'll wait more towards the end, and then we can kind of like add color and extend and fill in different things.
All right. So the why of clustering, is, as we mentioned a little earlier, we have this, dimensionality reduction in preprocessing. And the really cool thing about this was that I hadn't seen this before, is that you can actually include this clustering model in the pipeline. And you can use like a grid search CV to find like the best value. And here I mentioned the best value for K, and we'll get into that a little later as to what K is. You can also use it for semi-supervised learning, as we mentioned earlier, to kind of get this, you can train a data set from labeled clusters. So you cluster everything, you label it, and then you train your data set. And then there's this interesting idea that he brings forward about segmenting of an image. And he specifically references color segmentation as an example. And then we have like additional clustering information about like customer segmentation, as we mentioned earlier. And there's, data analysis that it can be used for, anomaly detection once again, and then search engines, which I think might be, no, that's not at all related to what you said earlier. Is it, Ryan? With BERT?
In a sense, yeah.
Okay, yeah. So those are some of the reasons why we might cluster. And then here's the part that I really wanted to bring up, which is like, and this is kind of towards the end of the chapter, but I wanted to bring it forward because of what we're doing here. If you look at this page here, you can see that there's a lot of different types of clustering models. Yeah, K-means, db-scan, agglomerative, Birch, mean shift, affinity propagation, spectral. There's so many. And I have a link here on the slides that you can run down Scikit-Learn and test them out. The gist is, for this chapter, we seem to have focused on K-means and db-scan. And then that's just something I wanted to bring like to the front, because that's kind of, when we have this many to go forward, sometimes you just have to pick a couple. And I think those are the two he went with, is K-means and db-scan. Now we get the history of K-means. He says that it's best, where I think I found that it was best described with this. And once again, we have a word I can't pronounce. Voronoi?
I think it's Voronoi.
Voronoi.
Voronoi. It is
Voronoi.
pronounced as Voronoi.
Voronoi. Okay. And so this diagram here is used to sort of represent what a K-means cluster looks like. And we learned that, originally it was developed in 1957 by a guy named Lloyd, but it was under copyright. So it comes back again in 1965, introduced all on its own by another guy named Forgy. So it's also known as a Lloyd-Forgy algorithm. And I just thought that was really cool, that it's not only is it that old, but it's been brought up twice. Around 2006, we got a faster or way of identifying the centroids of a K-means algorithm, and that was called the K-means plus. We have a couple of other varieties, such as the mini batch K-means, which is faster but has more inertia. And then it requires a number of clusters parameter, which is represented as a K value. All right, so that's a lot of information all at once about the history of K-means. And so okay.
If I could just do a complete, like, this is a total non sequitur, but just a complete aside. I think one of the worst things in science and statistics I find to be rife with this is when you just name things after people, because then there's no intuition around this. Okay, so if you say like there's the Hall-Forgy algorithm or whatever, it's like that means nothing to me, whereas at least K means I can create some sort of mental picture to try to remember what is this algorithm. And and so I find that actually the name K means really helps me remember what that algorithm is. And so I I would love it if somebody named something after me, that would be awesome and everything. But like scientists, I think as as a way of doing service to future learners, you should try and give it a more intuitive name and not just name things after people.
It
Let's all
comes
hold
from
Ted to that.
academia.
We got to hold
Okay.
him to that when the key algorithm is discovered, developed.
Yeah,
Well-
we'll see if I change my tune.
Well, you already
see,
have the,
in
they already
okay,
have the, yeah,
in
you already have the
academia.
talk, yeah.
Mhm.
You have
Okay,
the
can,
talk
can I
series
finish,
named after
please?
you.
In academia, you see, people don't get much money. They're only called to fame. And in very close, tight society is this name after theorem, after lemma, something like this, after method. So they're very partial to it.
Mm.
And I can sympathize. I'm just saying that, if you tell me, Fubini's theorem, there's just no intuition around it.
Yeah, and I can see that. And I can see how like the k-means, I mean, what does k mean actually, right? It's like, well, it's a number that I have to input that represents something. I forgot what. But when it's Lloyd 4G, you're just like, okay, who are these people? But it's cool because at the same time you get to learn who they are and then learn more about these theorems. But you also have to consider that what k-means has been through is quite a lot. It's had quite a lot of I guess transformations and additions to it since its original introduction, right?
Yeah, I'm just complaining because this is the pain I go through where I'm trying to learn about something and they'll say, oh yes, there's this statistical process you can use. But before you use the process, you should, and I'm just picking random names here, you should run the Leventhal test and you should also run the Rosenberg test to make sure that this is an appropriate thing to do. And if it's appropriate, then you can use the, Smith-Johnson, test. Like, what? None of it's just
Oh yeah, yeah.
gobbledygook for me.
Yeah, I know exactly what you're talking to. I just now forgot about every analytics test that I ever have to use. They're all named after people.
Right. So then it just becomes this horrible rote memorization. There's no intuition. And I wouldn't say that everything in math is intuitive, but you can try to say, what is a field? What is a group? But then as soon as you say, I've named things after people, so it's a Hermitian. Well, great, you named after a guy. That tells me nothing.
Yep.
Sorry.
I think it helps if you name the model and then maybe name which version of the algorithm inspired by who the scientist is. So like whenever I think of like k-means, like one technique I follow, it's two different scientists named Wong and Consenbar. So I'll say, oh, I'm running a k-means clustering, but if I specify like in my notes, I'm following the algorithms from Wong or Consenbar, I'm following their techniques. But I think it helps if you name the model first, because like if you say Pearson, I mean, Pearson came out with a lot of statistical mathematical techniques. Which one are you talking about? So I think adding more context, if you're going to use the particular technique of the scientist, it helps to name the technique first, then the scientist.
Yeah, like if I said to you a Pearson number versus a correlation number, I think one of those two has like a better intuition.
Yeah.
All right, sorry, I'm gonna stop my rant now.
That was cool.
We should call these the key naming criteria from now on.
I really, Ted, I don't know what you're complaining about. You got that whole talk series named after you, and I don't understand the complaint.
You have a talk series named after you? Okay.
No, he's making a joke about TED Talks.
TED Talks.
Oh.
Yes, I get no royalties from TED Talks.
All right. So there are some things you learn about k-means. I think the primary instruction we're given is to remember to scale the data. K-means does not do very well with data that's, all over the place. I don't think I know very many algorithms that do very well with data that's scaled all over the place. But moving on, cluster amount, I believe that's our K value. There are ways to finding this number of clusters that we need. You've got this thing called an inertia elbow chart. There's a silhouette line graph. There's a diagram. We've heard that this is a limited solution. I wrote the comment here. Well, we're all a little limited. There's things that it can do. There's things that it can't do. That's why there's probably so many clustering algorithms out there, right? We know that it doesn't perform well with non-spherical shapes. And I put in there whatever that means. And I say whatever that means is because, like, what do you mean by a non-spherical shape? I mean, you actually have to be able to visualize the data in order to identify whether or not it's a spherical shape. And that requires, I believe, a bit of clustering, doesn't it? Depending on the size of dimension.
Okay, it means not necessarily spherical shapes. They should be compactly distributed around the centroid. So it could be, for example, it could be, by the way, a square, a center of a square. But in general, we measure distance around the centroid, and it should be less than particular distance. Well, if there are no other centroids, in this particular direction. So they're actually limited with this radius. And when you do radius with a center, you get a sphere. So this is what they mean by spherical shape here. It is not actual sphere. Okay. It is just because they have a radius, which they measure from centroid.
Okay. Yeah, Kalika, if you go back to the Scikit-Learn that compares the different algorithms, you'll see there's one that has three sort of, they call them ellipses, but they're very elongated ellipses, the fourth row.
This one right here.
No, the one above it.
Oh, this one.
Yes. So k-means will not do so well with those because they're more oblong. Now, yes, you're right. We can't necessarily visualize it in higher dimensions, but in 2, we can say it's the difference between circular versus more stretched out. And in however many dimensions, it's still the same concept that whatever your distance metric is, like Maya said, you want them to sort of be compact and similar in all directions. And that's why the scaling that you mentioned is also important.
Yeah, so, and that would be this, yeah, like you said, the fourth row right here, which would be sort of this ideal shape for
that's
k-means.
The happy path for k-means is that 5th row.
Right. And then in order to acquire that, though, like, how would you be able to tell that this is the shape of data I have? I know in what I've learned is it's easier to just do dimensionality reduction and reduce it down to, 2 features and plot it. Is there any other way to manage that other than just trial and error, which is also what I'm used to doing?
I don't know if anybody here knows. I mean, I don't think you can perfectly know a priori. That's one of the themes that we've seen at different points in this discussion. You can't know the best algorithm, whether it's clustering or whether it's whatever. So you can't necessarily know a priori whether or not your data is very, I don't have a better word for it, very spherical in the different dimensions. The distance means similar things in all the dimensions, right? And in particular, not just what it means, but where your data points lie, So like if you're doing customers and, one of them is how frequently they come into the store, well, if you have the difference between people who come in 5 times or 10 times, that's a pretty reasonable spread. But if you have some people who go to your website and they buy 1,000 times, they're just like on a completely different scale from the people who buy 5 times, and that's going to give you challenges. So I think the best we can say, like very broadly, is if you have some intuition around your data, do you have a sense that the data is somewhat uniformly spaced? And in the book, they have the example where they have 2 clusters that are very dense, or 3, and then a couple that are more, larger radius, more spread out. And you actually will then see that, yeah, k-means maybe didn't do so well on the ones that are sort of further away. By our eyes, maybe most humans would agree that we should include those, in the more spread out ones. But k-means doesn't have that sense of intuition. It's just measuring distances. And so maybe it gets some of those wrong. And other algorithms may also have similar weaknesses, that if you have dense ones and spread out ones and you're trying to do them both. So the best we can do is sort of talk about these algorithms and say, do they do well if you have weird shapes? Do they do well if you have different densities? Do they do well if your cluster has some variation in it, right? Like it's all kind of dense, but maybe in some places it's double the density of others. Some algorithms will just split that cluster where in that region of slightly lower density. So at least we can talk about those strengths and weaknesses broadly.
Okay, I would like to add something. Please go back to this picture.
Oh, sorry.
So the low level, the low, yes, row, the very left example with a square. The thing is that if you apply k-means, I don't see k-means here for some reason. If you apply k-means to such kind of shape and you require 4 clusters, this you can get. I just experimented a lot with k-means, and this is the most, I think, the most high probability, the most probable distribution of cluster you can get with k-means on it. And they're not exactly round because they push each other, you see. They're too close to each other. But if they have their own centroids in the centers of squares, and if you measure the distance from this centroid to the all points, that this colored, for example, well, pick up your favorite color, then the colored points in the colored square will be the most close to it. Others will be closer to their own centroids. So this is how it looks like when, well, it is not, good choice of cluster numbers. Oh, well, but this is how it looks like.
Yes, it does, because that's another thing about k-means is that, we discussed it already, but this cluster amount, that k value actually has a huge impact on how your clusters are going to come out and whether or not you do get this sort of accurate, I guess, cluster that you're expecting or anticipating of the data. So they describe, I guess, our metric as inertia being used to identify the best solution. And that's the mean squared distance between each instance and its closest centroid. There's this idea where he kind of mentioned is getting lucky as a thing that you have to be aware of with k-means. And that's when you're looking at your centroid initialization methods. You're picking out where these centroids are going to be, and they can, in one type of algorithm, they're just picked at random anywhere. And then eventually they're going to converge, and that's going to be the answer you get. And then there's this k-means plus algorithm that was introduced in 2006 that took a completely different method. And so you're not just getting lucky anymore. That'd be like a kind of good way of like pointing that one out. Okay. And then you have your n init value, which it comes in with a default setting and determines just how many centroids should be selected for the optimal solution. And then if you know your initialization points for all the clusters, you can input this initialization parameter manually. And I think you set the n init parameter to 1. There it goes. Yeah, and that'll get you what you need. So there's all of that about how to use k-means. He actually gives a pretty good example in the book about the n init parameter and how and when to set it to 1 and under what circumstance. And it's really is, if you do know exactly where those initial parameters should be, then you can set them out. All right, this is a fun one because I looked at, he mentions there are 2 different kinds of clustering, right? There's a hard clustering and a soft clustering. And in hard clustering, one instance is assigned to a cluster, that's it. Soft cluster gives each instance a score per cluster. One example he gave was just the distance from the centroid. And he says it can be but it can also be a similarity score or affinity score, such as the Gaussian radial basis function, and refers us back to chapter 5. And then it said that the transform method can be used to gather the distance between each instance to each centroid. And he says, okay, that's in fact the Euclidean distance. So, and then he points out, okay, so I wanted to point out that the similarity affinity function that he mentioned is not provided in the GitHub solutions or the notebook that he provided. And the only information I could get from the infinity function was that the number of features will increase drastically with an extremely large training set. So I'm wondering, what does this mean for dimensionality reduction when we're working with this for clustering? Can we expect that, using this similarity or affinity function, would that be overkill or overextensive? And then over here in the left-hand corner, all I have is just what little I can find about the affinity function that he provided from chapter 5. Has anybody worked with this before? Do you guys know anything about it?
So I haven't worked directly with that, but I will say that in the past I've done stuff where, like, just looking at the difference between hard clustering and soft clustering, like sometimes you can do a method that gives you directly, like, this falls in cluster 1, 2, 3, 4, 5. But I've also done stuff with I don't know how to say it, but it's FAISS. It's Facebook's similarity search. And basically you can do a couple different things with that, where you can say, basically, like, return me the distance to the 5 closest points and stuff like that. And so that's kind of a form of soft clustering in a sense, if you're saying, like, I want all of the things that are similar to this one, and then it returns just the distances to all of the other points, because it's not necessarily giving you a single label to all of those points, but it's just telling you, here's how far away it is, and here's some other similar points.
Yeah, I mean, it's the difference basically between having just a hard single categorical variable, which is the class, the cluster, ID, versus more having like a feature vector. And so if your feature vector looks sort of like, 1, 0, 0, 0, 0, then that basically says, I'm really, really sure it's in cluster 1, right? But it at least allows you then to have things where you sort of say, like, hey, 0.5, 0.4, 0.1, 0, 0, so then you can tell that you think it's more likely in 1 than 2, but you're still not that sure. And depending on the algorithm, like, say, if you're feeding it into a neural network, it may actually appreciate knowing the difference between when you're sure and when you're not so sure.
Okay, that makes a lot more sense than trying to find out what a radial function is. Yeah, so you would say that there's a time and a place for both, and that one of them is not necessarily better than the other, but it's probably going to be more, what's the word? Larger than the other, right? More dense or complex.
Yeah. So Ryan, you've shared in other weeks a little bit about AutoML. So do you know, does driverless try to do any clustering in its feature engineering, or is that really a little too esoteric for it in terms of what it manipulates?
That is one of the options, but it's not frequently one that wins. So we have a whole set of transformers that it will try, and one of them is basically do clustering and then return those clusters as a feature, and that basically never wins. It is one of the things that's tried, but it's never really found to be useful. And we have a few different varieties of that, and it doesn't tend to help, because the distance itself is encoded in all of the features that you're going to pass in anyways.
Okay. Anybody else have any questions about hard clustering and soft clustering? So this one's going to be a quick slide. I didn't get a whole lot out of dbScan section. It mentions that you want to use dbScan. You're looking at continuous regions of high density. So you're not looking at spheres anymore. You're looking at areas where there's this amount of just dense populations. dbScan has an epsilon neighborhood, which is a count of the instances that are within a small distance from it. You get a minimum number of samples. If it has at least these number of samples, it's a core instance. And I think the rule is if you're in the same neighborhood, you belong to the same cluster, and you can include many core instances. So if there's a long running instance, you're all one. If it's not a core instance and is in the neighborhood, or what is it? If it's not in a core instance and it's not in the neighborhood, it's an outlier, which is represented with a -1. And there's no predict method in dbScan. They found that a classifier is better at predicting the cluster the data may belong to. And that would be the KNN example that's over on the right. And there's actually a link to his actual notebook there as to how he got this image to appear. But yeah, that was dbScan. And that's actually the end of the presentation that I got for you. So
Yeah, so one of the things that's interesting if you compare dbScan with k-means, right, is you don't tell it a priori the number of clusters you're expecting. It'll do it just based on the hyperparameter, based on contiguous regions that it finds. You can see obviously here the 2 moons data set, it has no problem with it. K-means would utterly fail because these are very, very far from round, circular spherical clusters. But the other thing that I think is particularly interesting about dbScan is you had it in the notes there, but it does not require that every point in your training set, in your unlabeled training set, be part of a cluster, whereas k-means requires that. So that's a very key difference. So if you had an extreme outlier, if you just have a bunch of points here, a bunch of points here, and I just add 1 point way over there, that is always going to get calculated into the centroid of some cluster, and it's going to significantly pull the centroid. And so if you have data that you're concerned about, that you actually have some kind of outliers, whether it's bad data, measurement, or just whatever, then you might prefer an algorithm that doesn't require all the points to get clustered, because then it'll basically reject ones that it says are just too far away, and those won't go into sort of the computation where the clusters are.
Always felt like dbScan has been is a little sensitive in those parameters for, I think it's the minimum number of samples in epsilon, where it's like if you don't get those just right, you are quite a bit in danger of the bulk of your data being interpreted as an outlier. And naturally, it's dependent upon what your data looks like, but that's just always been kind of my little experience with dbScan. I've seen some great things done with it. It just
Yeah, no, that's a great point. I'm actually just about to do a clustering project at work, and so I guess, you know, I'll have to really look at my metrics to make sure, to your point, that dbScan, you know, has good parameters and that I'm not just getting a bunch of garbage out.
So when you use a technique like dbScan, and do you usually use some sort of like grid search algorithm then, or some sort of, you know, where you have a series of, well, let's try this and let's try that, to knock things out or declare things an outlier? Or how do you?
In my experience, you just have to look at the data, because it's not something that you have an answer to necessarily. If you're doing clustering, you can't directly say, well, like, since you don't have the labels, you can't say, well, you got this cluster entirely wrong, or there's all of these outliers and they should have been here. So typically because it's unlabeled, you have to go through and you have to just kind of manually evaluate, does this look like reasonable clusters or not?
Well, you can use some like cluster performance metrics, like the silhouette score, for example. I think. Do they cover that in this class? In this chapter?
They mentioned it in the chapter, and silhouette score is decent, but it's a metric that isn't necessarily telling you that it found what you're interested in. It's just telling you how well represented your clusters are, like how good it was at actually grouping things up. So I silhouette score is useful, but I don't think it necessarily guarantees that it clustered it in the way that you're interested.
And I think silhouette kind of corresponds with k-means, because it's looking at distance. So if you have, like here, these 2 moons data set, if you have a cluster that's very non-spherical, then some of those within cluster points are going to be quite far away, but that doesn't mean that it's not a really good, accurate clustering.
Yeah, I mean, I mean, I think I don't know of like a metric, but I could imagine some metric where it's like more based on like local distances, like within like the cluster, that could account for that. Yeah, I'm just saying, like, you know, there's usually, I guess, like some metric that would give you a better idea of like the quality of like the clustering.
Yeah, well, I think like the author was saying, if you use k-and-n and it sort of agrees with your clusters, that's a good starting point. If k-and-n doesn't agree with your clusters, then you're in deep trouble probably.
Yeah.
But I was thinking, I think Jerry, you were the one that asked. So, you know, for epsilon, I mean, you could just chart, you could plot what number of points, you know, are going to fall within epsilon of given points for different values of epsilon. So if epsilon's small enough, you will get to where only the point itself falls within epsilon. So for 100% of your data set, so that's clearly it's epsilon that's too small. And then you can have one that I don't even know what metric you use, but for this value of epsilon, half the data set falls within, you know, my circle around of every point. And so that's clearly an epsilon that's too big. But again, not depending on how the data is scaled, you may not a priori know what that is, but you can do some EDA to say, okay, so it looks like, you know, this is the range, because obviously you want epsilon to contain a certain number of samples, but not a gazillion and not none.
And this would probably be one of those things where you had to do like a visualization prior to, you know, evaluating or as you're evaluating your data, right?
Yeah, I'm just saying, I think you
Results.
can evaluate the impact of epsilon without actually running the clustering algorithm, just by, you know, straight up seeing how many points are near each other point for different values of epsilon.
You know, I think I've seen that algorithm, but I forgot where it was. Oh, was it an algorithm or was it was just a function or something? But yeah, I think I know what you're talking about.
Yeah.
Now,
To-
I don't have a lot of experience with these, but I was wondering what happens in higher dimensionality spaces. I mean, we're looking, you know, the examples are obviously 2D or whatever, but let's say 3D. What do you do with, you know, real world data when you start pushing into the, you know, tens of dimensions?
Yeah, so once you get beyond 20 dimensions, you know, I think it's pretty much impossible to really kind of know. I mean, people do this stuff where they create the clusters and then they'll do like t-SNE or something, and they'll try to say, does it seem like when I do this dimensionality reduction, the clusters are sort of separated from each other? I don't
but then
know
they're
that you
creating
always.
artificials.
I know.
Yeah, you could have really good clusters that don't actually seem separated on a plot, you know.
Yeah.
But what I will say is, if the comment I made earlier about clustering is not, if it's not your end goal, if it's just an in-between step. So if what I'm doing is I'm clustering in order to identify certain customer types, and then I'm going to basically predict, you know, future sales to these customers, let's say, okay, then what you can do is you create these clusters. Those clusters create features for your regression model that's predicting sales. And basically that's the ultimate metric, is once you used those clusters, did those clusters actually improve the accuracy of your regression model? So you don't necessarily need to know a priori, do we think these clusters make sense? It's really, when they're not the end goal, then it's, you know, whatever. So like if you're doing anomaly detection, that's one of the few times where you are sort of directly saying, I'm going to use the output of the cluster. So if I use dbScan and dbScan says it's an outlier, then I'm going to predict that it's an anomaly. You can then take your test set and you can say, did it actually do a good job? So it's still kind of, it did the classification, but then you can use your classification metrics to say, how many false positives did I have on predicting, you know, my outliers, and how many false negatives did I have, and look at that. So again, because typically the clusters are not the end goal in and of itself.
I think at one point we were actually just looking, at least I can't remember like exactly if we were looking at centroids or what, but we were actually looking at, you know, what these clusters, or you know what these clusters came up with regards to the features, and we used like a heat map table to see, you know, okay, I think we were looking at basketball scores at the time, and you know, seeing, you know, this person has been performing extremely well on defense, and this person's doing very well on offense, and this is like, you know, a defensive player versus an offensive player, I think was the end goal, but like without, it was just like an exercise. So by looking at sort of the intensity of where and the similarities of where these are, you can get a good feel to whether or not you have a good sort of set of parameters for this, for your particular clustering algorithm.
I think there are
Okay.
a couple things to mention around clustering. I think the first thing is that there's a lot of domain knowledge and heuristics that and prior theories that need to occur before you do the any type of clustering. So typically, I would say a lot of times in the industry, it's mostly the marketing team. Oh my gosh, you support any type of marketing team. They're always trying to create some kind of cross-sell offers. The revenue team may want to know about customer retention. Some service team may want to know about client segmentation. And typically, when they want these models deployed, they're going to ask the professionals that kind of have some domain knowledge or to work collaboratively with domain knowledge professionals. So like whenever I do customer segmented models, I've spent like 2-3 years already doing all kinds of analysis on customers. So when it's like, oh, we want a customer retention model, I've already seen some of the trends within prior projects. So a lot of times you kind of have an idea of what features to bring into the model, and it makes it easier to interpret the results because you've worked with the data before. It's harder to do clustering if you're unfamiliar with the domain, because then you're more likely to pull features that may not give you meaningful clusters. So there is that prior heuristics and domain knowledge that needs to happen before you're given a clustering project.
Yeah, okay. So that's an emphasis on feature selection, right? And perhaps engineering as well, making sure that, within the domain knowledge, because you have this domain knowledge, you're able to make sure that you are selecting the correct features and not just throwing everything all into one mix of every piece of information that I have ever known within this, section or sector, and trying to get some information out of it, right?
I mean,
Yeah,
the other part is just with like domain knowledge is just interpreting the results, because like once you like cluster and you get like a bunch of clusters, it's probably important. With more domain knowledge, you have like a better idea of like, what those clusters could represent, or just what to look for in the feature space that like would define each of like the clusters that you get at the end as well.
Okay, I want to add to this something. There was a question about higher dimensions. DBScan, as I've seen in one place, mentioned does not work very well with very high dimensions. And one of the things, maybe something else, but one of the problems is when you consider radius, and when you have it to the 10th degree, for example, 0.3 becomes millions. So the volume of your sphere drops quite quickly in high dimensions. And actually, it is not only true for numbers which are below 1, which naturally, when you take them to higher degrees, tends to go to 0. But the formula for multidimensional sphere includes a factorial for number of dimensions, which means that even unit sphere will be dropping in size, will be dropping in volume. And so pick up correct epsilon becomes rather complicated in this situation.
Yeah, to follow up on the comments that Robert and Christy made earlier. So for the project that I'm working on, I'm expressly planning to exclude any demographic features from the clustering algorithm. And what I'm hoping to be able to do is to then, if I have what I hope are good clusters, to then see, are there any correlations with the demographics? So for the people who behave this way, do we see a pattern where they're younger, they're older? So like, I can tell you something that's like a no-brainer. We've predominantly done in-person medical appointments in the past, and now we offer telehealth once we started doing this when COVID hit, right? Well, I don't think anyone's going to be surprised to know that the people who prefer telehealth are average much younger in age than the people who prefer in-person instead of an online appointment, right? But so being able to find insights like that, that's one of the things that we're hoping to be able to do. So definitely, you know, I could build clusters on that, but that's not what I'm looking to cluster on. That's what I'm looking to learn with, you know, without looking at that information.
So you said, so Ted, in your paraphrase what you're saying, you're essentially working backwards from the problem. You already come with a predefined, I'm trying to find this out before you even approach the data.
Yeah, so basically I'm only going to give the clustering algorithm the features that I care about for clustering. So in our case, it's behavior around appointments. You know, you could theoretically give any clustering algorithm, whether it's dbScan or k-means, a million features, right? You could give it the person's height, their hair color, you know, whether the last digit of their social security number is odd or even, and eventually it will cluster on all of those different things. But it's because this is unsupervised. In a supervised learning algorithm, if you give a gradient boosting machine an extra column that's just complete noise, you know, whether their social security number is odd or even, it'll basically ignore that feature. Clustering algorithms don't know how to ignore features. They will use all of them. And so it's important that you give it just the features that are the behaviors that you want to cluster about. And so I'm a little bit worried about, like, well, which features do I give it? And am I going to overemphasize certain aspects of it versus others? You know, like, is it important to me whether or not people cancel their appointments? And if I put a lot of cancellation features in it, then I'm going to skew that model towards caring about that behavior. Whereas I could theoretically say, we care about these other things. We don't care if they cancel their appointments. And so then I shouldn't put any of those features in when I'm building my clusters. Does that answer your question?
Yeah, that was a good example. Thanks.
I had a pretty major clustering project I worked on a while ago. One of the old systems I worked on at my old job was we had these building blueprints, and on those blueprints, there's a whole ton of different markings, and those markings have all kinds of different meanings. And typically there's a legend somewhere, but even that isn't necessarily up to date. So you might have something that's marked as like L1, and that's lighting fixture 1, but then you have to make some mapping to like what actually is lighting fixture 1. And so in our workflow, people had to draw little bounding boxes around every single L1 and then define what it was. And that could take a long time if you're doing a whole hotel's worth of lighting fixtures, because there's all of these pages and then you have to find every instance of that lighting fixture. So we had a system that could basically try to find the rest of them after they drew a bounding box around the first one. But even finding the first one of all of the different assets, there can be all kinds of different lighting fixtures. There can all kinds of different electrical assets. There can be faucets and all kinds of other stuff. So just sifting through 200 pages of documents and finding every single symbol for all of the different assets can take a while. So one of the things that I tried to build was an initial, like, just basically asset finder model that would just look across all of the pages and just try to find every single asset, regardless of what it was. And then the hope was then you can have the user label that and say, oh, this is L1, this is a certain kind of lighting fixture. And so the first layer was finding all of the assets. And then the second layer was presenting that to the user and saying, you figure out what all of these are. This says L1, what does that actually mean? But part of the problem is if you have 200 instances of L1, you need to in some way derive, this is like the L1, not logo, symbol, and then have them only labeled that one, because you can't show them 200 instances of L1 and then expect them to sort of map all of those together. So we tried to do clustering on these little tiny image snippets for all of the different symbols. And I tried a whole bunch of different methods trying to figure out, is there some way I can basically take the pool of all of the assets and then cluster it, and then I can just present the center of the cluster or something like that, and then they can label that one and then apply it to the whole cluster. So if there's L1, L2, L3, and a bunch of other stuff, just present them a single L1 and say, what is this? A single L2, what is this? And so I tried a whole bunch of different methods. And like we were talking about earlier, the different hyperparameters can get drastically different results. So I tried a whole bunch of different algorithms. I tried a whole bunch of different hyperparameters, and I wasn't able to find anything that worked generally across a whole bunch of different documents. On each document, I could kind of tune it up and get a result that looked normal for one set of documents, but not another, and stuff like that. So that was my experience with clustering on that.
And that's a semi-supervised learning method that you're talking about there, right?
It was unsupervised. It was all of this stuff that we were looking at today, like that graphic that you had at the beginning with like affinity propagation and all of those kinds of things. That was something that I was looking at back then, was how do I figure out which one of these applies? And I basically just did a brute force search and just said, run all of these, and then I'm going to look at the folders and just evaluate, is this correctly mapping out clusters that look reasonable? So like, here's the L1s, L2s, A1s, whatever else. And I some of them worked okay in certain scenarios, but if I tried applying it to a bunch of different documents in different conditions, I couldn't get it to consistently work in the way that I wanted, at least.
If I may ask you, what kind of methods you use, what kind of clustering, and what was the size of your data set?
So it's all of those methods shown there, basically. Is I tried the full range. I just did a brute force search. I just said run all of these, and then I'm going to evaluate the folders. So what I had is I had it output the little snippets of L1, L2, whatever. I had it push it into their own folders under different subfolders, saying affinity propagation, mean shift, spectral clustering, etc. And then I tried to look within those and see if it was reasonable clusters or not. But the data set itself was in a single set. I could have 1,000 or so assets, and they were images that would range from 14 by 14 to maybe 28 by 28. So they were fairly small images, but it's still pretty high dimensionality when we're talking about clustering. That was something that was mentioned earlier. When you go really high dimensionality, it kind of muddies things. One of the things that consistently showed up in my clustering was if you have some sort of occlusion. So like on building plans, you have a whole bunch of straight lines and like dashed lines and stuff that might intersect your symbol. And so I would end up with clusters that were reasonable clusters where it was like, oh, these clusters all have the same straight line in one spot, because it's like a row where it's like all of the L1s got intersected by a straight line that just went through all of them in the same spot. And then those all got placed in one cluster, but they clustered based on the vertical line that was inside of them, not based on the symbol itself.
When I start off like performing clusters, I use like different techniques. So I think one of the things that I'm not sure if it was mentioned in this book, but I remember reading a long time ago that the way you approach clusters is it's not really a single algorithm, but like a set of algorithms which help define like the business problem. So it is multiple types of algorithms that you would use to get to meaningful clusters. So after I have my features, one of the downfalls of clustering is that the algorithm will do whatever you tell it to do, regardless if you have any meaningful clusters in your data. So when I have all of my features that I'm going to use, I run a Hopkins statistic test first. So this is a technique that came out in 1990. And what it does is it assesses the probability that your data set is generated from a uniform data distribution or a non-uniform data distribution, and it tests like the spatial randomness of your data. And how it works with the threshold is that, it'll return a threshold of 0, ranging from 0 to 1. If you move beyond like 0.5 or closer to 1, then it means that it has detected significant types of clusters in your data set. If it's close to 0, then it means that you pretty much don't have any meaningful clusters to even do a clustering analysis on. So and I use that first because that helps me before I even get started with the modeling, seeing, okay, do I have meaningful clusters or not? After I do that, one of the techniques that I learned a long time ago, like if you're doing k-means, where you're selecting k, always start with odd numbers and not with even numbers. So naturally, for clustering model, since your Hopkins statistic determined that you have more clusters, I don't use 2, 4, or 6. I start building clusters with like 3, 5, and 7. And then after that, when it comes to evaluating the model, I use 4 different techniques for evaluation. So the first one is just visualizing the clusters. But what I do is I create an elliptical star visualization that shows me how my cluster spits out the points and how they're connected. And then I used, for evaluation, I used the silhouette and the elbow, which the book mentions those techniques. But then I use a newer evaluation technique that Stanford University created called the gap statistic. And what I'm looking at is, so visually, I'm looking to see, okay, is 3 or 5, what is the optimum number of clusters? Because I don't want to see clusters on top of the clusters. You should be able to see some separation in how they cluster. If you just see a bunch of clusters on top of each other, then you have too many. And then when it comes to silhouette and elbow, I like to see, okay, what is their ideal number? If silhouette says 3, does elbow say 3? They should be around each other. Like if one says 3, the other one says maybe 4 or so. Okay, then you kind of make a decision on what you want to, which, meaningful clusters you want to use based on looking at your graphic, but it shouldn't be far away. Like silhouette shouldn't say 3 and the elbow shouldn't say 7. That's very far away. So I use silhouette, elbow, and gap, and typically I kind of do a weighting. So most of the time, silhouette and gap might be like aligned with the number of clusters, and maybe elbow won't. So I kind of look at those 4 evaluation techniques, but I'll definitely recommend that if anyone's clustering, research Hopkins statistic and try to assess that you have meaningful features first, and then research the gap statistic method for evaluation by Stanford and compare that with silhouette and elbow when you're running your models.
Would the Hopkins statistic work in this like first row example where it's like kind of not typically what you would typically think of as like clustered data,
Right, yeah. So it'll help assess that, and it'll give you an actual value, whether or not ranging from, like when I build it in R, the threshold for me is if it's over like 0.5, ranging from 0.5 to 1, then I know that the data set has meaningful clusters. It won't tell you how many it has, but at least let you know that you do have meaningful clusters in your data set. And then that's where you do the other evaluation techniques. Like, you know, you visually want to look at the clusters, and that's when you leverage like silhouette or elbow and the gap statistic if you're doing k-means. Now, the gap statistic, when Stanford created that evaluation technique, that will work on hierarchical agglomerative models as well. So that doesn't just work on k-means. They actually created that to work on all different types of clustering algorithms for evaluating the number of clusters.
Okay, thank you very much. Can you please put it at the end of your slides? It would be fantastic. You know, what kind of methods could be used for definition of a number of cluster. And I would like to note that, okay, I was working on estimating the best cluster using elbow methods mathematically. You can, you know, measure the angles using mathematical means. And I wanted, okay, actually, I wanted to submit it for Scikit-Learn, on which they replied to me, but that they have much better method for this, which unifies several different methods for such kind of goal. And they showed to me, and yes, in developer stage, they have fantastic method which does it, but it is still in developer stage. The last commit was 2 years ago, and I asked for them to add me to the developers, and I got no answer at all. So, but I can show you something about the elbow method. It depends on the scaling of your, can I please share my screen? It depends on the scaling of your variables. So here's the elbow method for some, okay, why it does move? Okay, here's the elbow method for some clustering. And right now, the most possible angles could be 2 or 3. But if I stretch this axis and cut it, for example, somewhere here and get the plot. Okay, this is, sorry, my initial. This is the initial plot. Then I start to stretch it. And you see 2 is not good anymore, but it looks like 3, 4, or 5 could be reasonable, or maybe 9. Then I stretch it a little bit more, and 3 is not good anymore. 4 drops out too, and 5 doesn't look very good. Actually, 9 is the best here, and yes, the 9 is the best number here because here are my clusters.
When you say stretch it, what do you mean by that?
I mean that actually visualizing with elbow methods is not very reliable method.
Did you by any chance try the, I think it's called the silhouette charting method, where it shows you the different silhouette scores in like a chart graph with the representatives is, I guess they look like hills?
No, I didn't try silhouette. Yes, I understand what you mean. No, I didn't try silhouette method. I wanted to work with elbow methods. Okay. And I wanted to make a complete methods which shows, which computes what is the best clusters for elbow method.
Okay. So the complication is sometimes within not the method so much is how you visualize that elbow chart.
Yes.
Yeah, you can obviously have a computer measure the angle. You don't have to just eyeball it, right? So we're at the bottom of the hour, and one thing I just wanted to mention is if you guys are interested in this idea of clustering and you want to do a little bit more reading, you can certainly read more about clustering. There's tons of literature about that. But one of the things that I've seen, some of the trends right now, is that if you think about dbScan and sort of drawing a circle around each point, you're sort of pairwise comparing the points to a large degree. That's the extent of what you're doing. And I'm seeing more and more literature now about people using graph representations of their data. And so now, instead of just saying sort of in terms of your immediate, neighbors in a graph, let's also take into account sort of the features that are in the graph, but that are 2 hops away, 3 hops away, and trying to factor in the global architecture of that. And so there are a number of, they don't call it clustering, I don't know why not. It's usually called community algorithms for graphs. But so you can look, for example, at like Louvain modularity and compare that to dbScan. And so if you have other features and you can sort of represent your data, not just tabular IID, but sort of in this graphical nature, then the idea is, generally speaking, that you're getting data from not just sort of your 1-hop neighborhood, but you can sort of try and pull in more global, the word's escaping me, architecture is not the right word, but the global structure into how you're defining your communities, your clusters. So I thought I would just share that in terms of people want to do more reading.
Yeah, I've like, I guess in my work, I've mostly for like clustering type analyses, I'm mostly using like graph-based like clustering methods like Louvain. I think newer one would be like Leiden. So I guess like it's kind of just been a standard in, I guess, like the field of like analyzing like sequencing, like single cell sequencing data, but I'm not exactly sure why. I think it's mostly just like, I don't know, probably like accounting for or like a complex like feature space or something like that. But yeah. And also like one thing that I've like sort of been interested in is that with like graph-based like clustering methods, you can kind of there are ways to cluster, I guess, like multimodal data sets where you have like different sets of feature spaces. I guess like, I don't know what a good example of this would be, but maybe with like patient data, you might have like health record type data, but you also might like have some like patient tests where you like, I always think of like sequencing data, like you like sequence like, I don't know, you like take like a blood sample and like sequence it. And that's like in a totally different feature space than, let's say, like, I don't know, their normal like electronic like health record type data. So like with like graph based clustering methods, you could essentially like construct, I guess, like 2 separate graphs in each of the feature spaces and kind of like cluster on those like simultaneously, which, I don't know, that's like something I've been looking into and been interested in recently.
Yeah, thanks for sharing. Yeah, I think I think that gives good color to why it is that people think that things they do on these graphs can potentially go beyond what you would do with just a straight k-means or dbScan. Like, even if we don't go into all the gory details, I think it just you can start to see like there's these options, there's different things you could try. And again, it's that looking more for global structure in a graph. If you look at like the half moons data set, if you imagine that there was some kind of graph on it, you might be able to very quickly see there's very high connectivity within each of the moons. And there may be some connectivity, but a very low degree of connectivity between points from one moon to the other moon. And so a graph algorithm, even a very simple one like label propagation or something like that, might just crush it with something like the half moons data set if it were if you had good, graph information that gave you that connectivity structure within each of the moons. All right, anybody else? Any last questions or comments before we close out the book club for today? All right, awesome. Thanks, Kalika. Thanks for being our discussion leader today. And I will say thank you also for volunteering to not just lead one discussion, but actually to do 2 weeks in a row. So very different vibe when we start talking about Gaussian mixture models. And so that's going to be our topic next week. And then after that, just previewing, we are going to take a break with the holidays and stuff. And after the New Year's, total sort of shift of gears, we're going to get into neural networks and deep learning. So we've been really mostly talking about Scikit-Learn. And so after the new year, it's going to really be about Keras, and it's going to be about building neural networks in TensorFlow. So I hope to see you guys next week. And then again, we'll kick things off sort of in a whole new direction when we start talking about neural networks.
All right. Thank you, everybody. And look forward to seeing you next week for Gaussian mixture models.
All right. Thanks, Kalika. So we're going to shift gears.